Okay, so this is 3.1 word problems. And so what we're dealing with is compound interest. So compound interest formulas. So the compound interest formulas will be on the problem type. So just like it is on here, the compound interest formula will be given to you by the problem. So the only thing you really need is you just need to know what number substitute in for what variable component, because all we're going to do is substitute and simplify. So the A represents the accumulated value, which is what you're looking for. The P represents your principal amount, so that's what you invest. That's what you invest. The R represents the rate, which is the percentage. The N is going to represent the number of times compounded in a year. And then T represents the number of years, or the time, I should say time in years, okay? So everything is just substituted into the variable component that it represents. So like on this first problem, and I hope you can see it, but if you can't, I am going to read it to you. Find the accumulated value of an investment of $11,000. So $11,000 is my investment, that's my P, at 3%. So remember the percentage is the R, which is the rate, compounded annually. So that word compounded annually. So once it tells you the number of times it's compounded, that's your N. And then for 18 years would represent my T. So identify what your variables are from the given values they give you in the problem. So compounded annually, well, how many times a year would that represent? So compounded annually would just represent one time a year. So when I put this into the equation, into the formula, and I'm going to use this formula here, okay? So this formula is only used, so we have A equals 11,000 times 1 plus 0.03, which is the 3% in decimal form, over 1, which is our N, raised, this is the caret, so for your calculator, to the 1 times 18. And then you just push all of that into your calculator, and your calculator calculates everything for you. So the most part of this section is making sure you can put it in the calculator correctly. And you should put it in the calculator exactly the way it looks on the screen. 1 times. So when you raise it for the exponent, make sure you put them in parentheses. So we get A equals $18,726.76. So you should make sure that you are rounding to the correct percentage decimal point. So it's money, so we round to the hundredth place or to the cents, okay? All right, so let's do another one. So number 2 has find the accumulated value of an investment of $7,000, which is our P, 5%, which is R, compounded semi-annually. So this is our N. How many times a year is semi-annually? It means twice for 11 years, which is the T. So when we substitute it in, we're looking at 7,000 times 1 plus 0.05 over N, which is 2, raised to the 2 times 11. This is the times. And so then we would just calculate that in the calculator. 1 plus 0.05 divided by 2, close parentheses, caret, open parentheses, 2 times 11, close parentheses. $12,051, because when we round to the hundredth place, we get nines. So it has to go up to the 1. So 12,051. And this is money, so we can put our dollar signs. All right, so let's look at number 3. Find the accumulated value of $400 investment, which is our P, 12%, which is the rate, compounded quarterly, that's the N. Well, how many times a year is quarterly? 4 times a year. And then the number of years is T. So we're looking at 400, open parentheses, 1 plus 0.12 over N, which is 4 in this problem, raised to the 4 times 4. So 400, open parentheses, 1 plus 0.12 divided by 4, close parentheses, caret 4 times 4, close parentheses. $641.88 is what we get. Okay, so you just go through and they're going to give you all the information. They're going to give you the formulas. You just have to know what to put where. All right, and then for the next one, find the accumulated value of an investment of $2,000. That's P. 9% is R, compounded continuously. So this is where the other equation comes into play. So the other formula is what we need, because anytime you see compounded continuously, there is no N, because it's compounded every second of every day. So compounded continuously uses a totally different formula because there is no N. So we have a P, we have an R, and then we know 5 years is T. So PR, N is irrelevant because it's compounded continuously. Remember, N represents number of times compounded in a year. But if it's compounded all the time, there is no N present. So we use a whole different formula, which is A equals PE to the RT. So remember, E is a constant on your calculator. So we're looking for the accumulated value of a principal amount of $2,000, which is our P. Remember, E represents the natural base, E. So that's just a constant. And then it's raised. So I'm going to put a caret to the R. For this case, R is 0.09 times T, which in this case is 5. So this is number 4. So this is straight calculation. So 2,000. Remember, the E is on top of the ln. So when you put it, it's going to automatically open parentheses for you. So 0.09 times 5, close parentheses. We get $3,136.62. And that's it. So that's a compounded continuously. Okay. So then number 5, find the accumulated value of an investment, $5,000. 5% is the rate, compounded monthly. So that's the N because it's monthly. So how many times a year is monthly? That would be 12. And then 8 years is the time. So A equals 5,000 times 1 plus. Remember, I have to go back to the other formula because I have an N now. It's compounded monthly. So that's 12 times a year. So I'll plug it back into my other formula, and then we're just going to calculate it in the calculator. 1 plus 0.05 over 12 raised to the open parentheses 12 times 8 close parentheses. So we get $7,452.93. You need to make sure you can calculate. If you're not getting these calculations, you're just putting it wrong in the calculator. So you just need to see what you're doing in your calculator. And then number 6 is a compounded continuously. So that just goes back to the other formula. So my P is 1,000. E raised to the R, which in this case is 0.07, times T, which is 6. So 1,000 E to the 0.07 times 6. So we get $1,521.96. Okay. So your formulas are going to be given to you. You just have to know what variable, what number represents what variable, and you substitute it into your formula, and then you simplify accordingly. And that's it. So that's compound interest. So those are your word problems from 3.1. Okay? All right. Next. Okay. So here we have these word problems, and these deal with growth and decay word problems essentially. So they can deal with population, they can deal with other types of substances, radioactive material, a lot of different things you can do with it. So these are considered growth and decay model problems. And so I'm just going to basically tell you how you're going to substitute in your information, and then you just solve for whatever the variable is you need to solve for. So the only thing you really have to understand is that a sub zero, anytime you have a sub zero as a subscript, is considered to mean the initial amount. Initial amount. Shoot. All right, let's try these again. So a sub zero is always an initial amount. Okay, and then a is a final, like what's left. Final amount, what's left. And then your x represents time. So t or x will represent time, and they'll tell you in the problem what it represents as well. So here, for these particular problems, the ones you're going to deal with, they're always going to provide you with some function that you're working with, or some quote-unquote formula, essentially, is what they're giving us. So they're giving us this function, a equals a sub 0 e to the negative 0.0077x for number 7. And they're basically telling us that this is the model used to determine how long radioactive material will take to basically dissolve or decay, essentially, right? So we know that's one of the issues with radioactive material, is that it's not biodegradable. So essentially, when they're trying to discard of radioactive material, they bury it in some concrete vault, and they try to figure out how long it's going to take for the material to decay or to dissolve, essentially. So we have a model, and you have models, different models based on that particular radioactive material. So we have this given model here, and they're telling us that if 400 pounds of the material are initially put into the vault, so that initial 400, should go in for the a sub 0. How many pounds will be left after 50 years? So the x represents the number of years since the material was put into the vault. So your 50 is going to represent your x, or your time. Your 400 is going to represent your a sub 0, because it's the initial amount. And what we want is how many pounds will be left. So that's our a, because a represents the final amount, what's left after some amount of time. So using the given function that they provided us with, we have a equals a sub 0 e to the negative 0.0077x. So I'm going to substitute in. I'm looking for a. I know a sub 0 is 400 equals negative 0.0077 times what? 50. So you should always make sure that whatever is your exponent goes in parentheses, because it's multiple components. So this is just straight calculation here. So you put this straight in your calculator. Remember, E is a constant. So 400 second ln, open parentheses, negative 0.0077 times 50, close parentheses, equals 272. So we're really just going to round to the whole. We're going to round to the whole. So A would equal 272 pounds. So I need you to understand what's happening. They put in 400 pounds of this radioactive material into the vault. They leave it in there for 50 years. It's still 272 pounds of it left. Okay? That's exactly what you're figuring out. So after 50 years, it's still going to be 272 pounds left of that radioactive material in that vault. That's what these problems are for. So a lot of times it's like, well, what am I going to ever use this math for? You may not ever use the math, but there is someone in their position or whatever job they have that can utilize the math. So these word problems and these application problems are just to show you this is how the material can be utilized in real life and in real world situations. And considering it's Earth Day when I'm recording this, I always find it poignant that this is the last thing that we do in the spring semester, because it always falls around Earth Day. Like, this is no way to protect the earth, but they have to literally figure out how long they can leave this material buried, because you can't cultivate the land when you have radioactive material buried in a vault underneath it. So they have to be able to know how long before they can actually build on top of that land. After 50 years, 272 pounds of it, you still can't do anything yet, right? Because it's too risky. So you just have to realize that even though you may not utilize this type of math, someone does, and it does come in handy. So then the second one, we have a new function given to us. A equals a sub 0 e to the negative 0.0099x for some new radioactive material. 300 pounds are placed in the vault. How much time needs to pass for only 91 to remain? So 300 pounds are placed in the vault. That's a sub 0. How much time? That means we're looking for x. Will need to pass for 91 pounds to be remaining. Remember, whatever's remaining or what's left is the a. So we're looking at 91 equal to 300 e to the negative 0.0099x. So on this particular problem, we actually have to solve for the x. So there's actually work we need to do. So what happens on this problem is, this is basically us trying to solve an exponential equation, because our variable component is in the exponent spot. So that's how you'll know when you're trying to do an exponential equation, right? So in the previous section, 3.4, we learned how to solve exponential equations. So the first step says you have to isolate the exponential expression. So the exponential expression is the base and its exponent. So that means I need to move the 300. So I'm going to divide both sides by 300. So we're looking at 91 over 300. Remember from the previous video that you should have watched, if it doesn't divide evenly, you have to leave it in the fraction form, because you have to have an exact answer before you approximate. So 91 over 300 equals e to the negative 0.0099x. So how do we get the x to come down? How do we get the exponent to come down to regular level? So what we do is we bring in what? The natural log. So in order for us to bring the exponent down, we have to bring the natural log in so that we can apply the power rule. So we bring in ln of both sides. And when we do that, the rule tells us that ln e to the x is just what? Just x. So my exponent just becomes my term, essentially. And so then if I'm trying to solve for x, that means I need to get x by itself. So I would divide both sides by this coefficient. You should not care that it's decimals. You should not care that it's negative. You should be following a process. So now this would be considered our exact answer. ln of 91 over 300 divided by negative 0.0099. But we are doing a word problem, so we need to approximate. So we're going to put this in the calculator. ln of 91 divided by 300, close parentheses, divided by negative 0.0099, and that gives us 120.4. So 120 equals x. So how long will it take for only 91 pounds to remain in the vault? 120 years. 120 years. That's why radioactive material is so damaging to the planet. You can't get rid of it. 120 years and there's still going to be 91 pounds left. That's big. And so you just have to understand that even if you don't care and you don't use it, the information is useful. Okay? All right. So let's look at some more. All right. So if we look at number 9, we're using the same function, and it's really just like 7 and 8. So in this one, we put in 300 pounds, and then how many pounds will be left after 80 years. So we're substituting in for a sub 0 and for our time. So A equals 300 e to the negative 0.0099 times what? 80. And so we put that in parentheses so that we can make sure we calculate it correctly on the calculator. And then we punch in our values. And the calculator gives us A equals 136 pounds. Remember, round to the whole. So after 80 years, it's still going to be 136 pounds left of this radioactive material in the vault. Okay? All right. So number 10 is another where we're solving. So we have the given function here. 300 pounds are put in the vault. 92 pounds left. We want to know how much time. So we're looking for 92 pounds to be left. We put in 300 initially. We're using this function 693 times x because we are solving for x here. So remember, you're solving an exponential equation. So you have to isolate the exponential component first. So 92 divided by 300 equals e to the negative 0.00693x. And then once you do that, you have to take the ln of both sides. So we ln and so when we do that, this is where we are. We would divide by that negative coefficient on both sides. And so we do that, and then everything goes straight into the calculator. Remember, you must have an exact answer first before you can plug in the calculation. So we get 171 because you get 170.5. So it'll be 171 years in order for 92 pounds to be left, right? So what would they need these calculations for? Because they bury those things in the mountains and in vast empty land that eventually they're going to populate with strip malls and neighborhoods. And so they have to be able to figure out how long before they can actually utilize the land above where they buried the radioactive material. So again, you may not find it useful, but it is very useful material and information. And then number 11, we're looking at population growth. So the value of a particular investment follows a pattern. Oh no, this is still this is investment growth. So online, you may have some population, some investment growth, but the growth and decay problems are all work the same. They have to give you a model, and then they have to tell you what they want you to find. So we have a model, the particular investment, the value of the investment, T years after 2000. This is important. T years represents the number of years after the year 2000. When will the account be worth $11,790? So we're looking for T here. So we only have two variables. We have A, which is the amount that we are going to end up with after the amount of time, and then T, which is the time. So let's look at what happens. So we have this given function, which again, they have to provide you with something to work with. So when would the account be worth $11,790? So $11,790 equals 9,500 e to the 0.054t. So we're trying to solve for time. So we would divide both sides by 9,500. And if that does not divide evenly, you will leave them in that form. So then 11,790 over 9,500 equals e to the 0.054t. We bring in the natural log. Which would just be 0.054t. We divide by that on both sides. And so when we do that, we get ln 11,790 over 9,500, close parentheses, divided by 0.054, and we get t equals 4, round to the whole. So t is 4. That's 4 years. Remember, time represents the number of years after the year 2000. So if t is 4, then when, not how long will it take to be worth 11,790, when will it be worth 11,790? So if t is 4 years, and we're looking for when, which is what year, it would be 2000 plus 4, which would be the year 2004. Okay, so for that particular problem, there was just a little extra in the way you had to answer the problem. So those are your chapter 3 word problems.